So today we start our last module, Module 5, Advanced Data Structures, because we are very close to the final. We only have 2 classes left, today and Monday next week. Yeah, only 2 classes left. Yeah. So for Module 5, we can only cover 2 topics. Yeah. Today, 1 topic, Heapsort. On Monday, another topic, hashing technique in the first half. I'll just give you a short introduction in the first half. Second half, we will do review for final. Yeah. So that's the plan. Then Wednesday, next week, 1 week from today, this time. So you will have in-person final. Okay, yeah, just prepare for it mentally. Yeah. The rules. Yeah, you haven't asked me the rules, right? The rules: open book, open notes, and you can bring your laptop. You can access our class notes, yeah. All our course materials you can access when you take the test. You can use calculator, online calculators, although we do not have very difficult calculation work. Yeah. We will not have complicated computation work, but you can use any calculators. But what you cannot do using your computers, 1, you cannot use search engine. Search engine you cannot use, okay? And any technical online forums you cannot use. And AI tools you cannot use. Okay. Yeah. What you can use only our course materials and online calculators. That's what you can use. Yeah. Other things, any communication software you cannot use. Okay, you cannot send or read messages through any software tools. Yeah, you cannot do that. Yeah. Yeah. So that's the basic rules. Yeah. Yeah. Let me read. Yeah. All right. So let me read the messages. Are you allowed to use personal? Yeah, definitely. You're allowed to use your personal. Yeah, that's why I said open book, open notes. Yeah, open book, open notes you can use. So then another question, yeah, right, yeah, any file format, okay, yeah, any format, notes, so Word, whatever, PDF, any format, all legal. Yeah, just if the content. Yeah, so here format is not important. If the content is about this class, all the material, all the study materials, okay, any study material you can use. Yeah, even your own study material you can bring. Okay, yeah, because some students they may do the online search study. Yeah, so you can even bring your own study materials, all legal. Okay, yeah, yeah. Let me know. So if you have any question, yeah, computers, notes, all those things. So that's what I can think of. Yeah, all those things. Yeah, but the bottom line, yeah, 2 main things you cannot use. 2 main, yeah, comprehensive. Oh yeah, all right, yeah, that question, yeah, I forgot. Non-comprehensive, okay? Yeah, not comprehensive. You only focus on the materials after the midterm, okay? Module 4, Module 5. Module 4, Module 5, actually Module 4, that's the main part, yeah, approximately 80%. 80% of the questions come from Module 4. Only 20% of the questions from Module 5. Yeah. Yeah. And, definitely the knowledge, so the question types, I will not give it directly from the part before the midterm. Yeah, but we need to use the knowledge, right? Yeah. So because definitely we need to use a lot of methods, theorems, results from first 3 modules we need to use. But the question types all after midterm. Yeah. 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 So mainly you based on your homework assignment number 2. Yeah. Let me see next question. Will the quiz part of the file be open to take the whole? Yeah. All right. Yeah. May not be the whole week. Yeah. Good question. Or we'll be doing both. No. Yeah. All right. That's a good question. Yeah. 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 I'm glad you, Michelle, you raised this question. Let me answer your question. Yeah. All right. Let me write something here. Yeah. Yeah. That's a very important question. Just to let you know. So the answer, yeah, part A, part B, we separate. Yeah. So let me write the dates. Yeah. The time. Yeah. All right. Part A, that is our quiz number 6, our last quiz, 10 questions. Yeah, but first, not the same time, okay? Yeah, so part B, yeah, part B. Part B easy, yeah, I think part B you have no question. Let me write part B here. 15, still 15 computation questions. All right, so that's the June 6th, Wednesday, from 5:30, 8 p.m. At Anheuser-Busch Hall, 002. All right, yeah. So that's part B, easy. Part A, I will give you this period, not the whole week, yeah. I mean, because the reason in our final, we won't have that 1 week long, okay? We won't have that 1 week long because I need to finish the grading. I need to submit a grade. There is a deadline. So we won't have 1 week long period. So the maximum amount of time I can give you, that's the final period listed in the school calendar. Yeah. If you look at the calendar, the final period, what's the final period? Final period from Wednesday. Yeah, this is starting date of the final period, and the end date 9, Saturday. Let me see. Is this a Thursday, Wednesday, Friday, Saturday? Yeah, Saturday. That's the final period. So for the quiz 6, I give you this is the period for your part A, quiz number 6. Okay. Yeah. But Wednesday, because I want to start it, the starting time. So this is, so start it right after part B, okay? Right after part B. Yeah, because before the starting time, I would like you to focus on part B. Yeah, because part B much harder. Part A, so easy. Yeah, for most students, it's pretty easy. So you do not need to worry about part A before you finish part B. Yeah. So I set the starting time after you complete part B. So then the quiz number 6 gets started. Yeah. At 8 o'clock. At 8 o'clock, I set that time. Then you have plenty of time. Yeah. You have plenty of time. You know, before Saturday, just submit it before Saturday. Yeah, yeah. All right. So that's the, you know, important information. Yeah, yeah. Any other information, just let me know. Yeah, yeah. This is important. Yeah. All right. Yeah. So let's start our part A. Heapsort. Yeah. So this is our sort number 6, sort algorithm number 6. Yeah. The last one for this class. Yeah. Actually, I have another interesting sort I can talk about, but for this semester because it is too short, so I couldn't talk about that. So it's the counting sort. I mentioned that before. I mentioned this name before. Yeah, but I cannot find time. Yeah, because I need at least 45 minutes to talk about counting sort. Yeah, but I won't have that much time. Yeah, yeah. So for this short semester, I just skip that counting sort. Yeah, yeah. Very interesting. Yeah, yeah. All right. Yeah. So we. Yeah. So I try to complete this heap sort topic today. Yeah. So this PowerPoint notes, the file, relatively long. Yeah. But I try to complete it today. Yeah. All right. Let's start introduction. All right. So the same problem we did many times. But this time, when we do it, we need to consider some special requirements. Yeah. And in your real-world applications, yeah, because some students worry about, you know, so because many questions when you work on, yeah, I can understand. Many of you talk about why we work on these difficult, challenging problems. Yeah. How large is the chance in the real world to have the similar problems? Yeah, I explained last time. Yeah. The most important thing is the problem thinking training we need to get from these problems. Yeah. Definitely, the chances that you work on the similar problem in the real are very small, but the problem thinking methodology, you know, that kind of thing you need to use a lot. That's more important. Okay? Yeah. So you just treat what we are basically doing here, we get a training in problem solving for computing problems. Yeah. All right, here, special requirements. Because in the real world applications, you need to consider many special requirements. Yeah. So that means when you apply one of the sorts, you need to choose the right one. You need to consider your special requirements to choose the appropriate one. Yeah. Here, let's look at what kind of special requirements. The first, we want to avoid very poor worst case, right? So very poor, I mentioned before, that is the big theta of n squared. We want to avoid bottleneck. So that's the bottleneck. Okay. Yeah. So the worst case efficiency must be controlled in big theta of n log n. Yeah. So for the 5 sorts we have learned at this point, only merge sort satisfies this condition, right? Yeah. Quick sort does not satisfy this condition. Yeah. So here, you cannot choose quick sort. Okay? Yeah. So this first requirement eliminates quick sort. Another one, yeah, other 3 sorts. Yeah. Selection, bubble, insertion, you cannot use. Only merge sort you can consider. Right? So one requirement, only merge sort satisfies this requirement. Second one, yeah, in place. I explained the meaning of in place last time, right? That is, yeah, just remind you, the extra space used. We only look at the extra space used. So what's the extra space? We do not count input-output, space occupied by input-output data. Yeah. Extra, other than input-output, the extra space used must be big theta of 1, constant, by certain constant. Yeah. So this is the second requirement. Yeah. Then you can see merge sort does not satisfy this condition. Merge sort. Yeah. If you recall the merge sort, first, the merge operation, look at the merge operation. Merge operation, we need to use 2 auxiliary arrays. Remember that A subarray, B subarray, we need to copy. We need 2 auxiliary arrays. That's the extra space. Yeah. That's one thing. Another thing is, other than the extra space used in that merge operation, you also need to consider recursion, right? Recursion. Yeah. Because the quicksort, for the quicksort, if you recall quicksort we learned last time, the partition step does not use too much extra space. It is in big theta of 1, but that's just the one partition step. It uses recursion. Recursion, there is a stack problem, right? Yeah. So there is some, potential big stack used in memory. Yeah. So the quick sort, merge sort, because you need to use recursion. When you need to use recursion, this step uses too much space. Yeah. Recursion step usually uses a lot of space. Yeah. For that reason, we cannot treat it as in-place algorithm. Yeah. But here, in place, to get it in place, here you know the idea. We need to avoid recursion. Okay? To get it in place, we need to, so here, the problem, avoid recursion. Okay? Yeah. In our implementation, avoid recursion. Yeah. Yeah. All right. Number 3, maintain dynamic data efficiently. Yeah, so this is another important requirement. Dynamic data. Here we need to consider dynamic data. Yeah. Data keeps coming in. Yeah. Coming in and go. Yeah. Insertion. So when you maintain your current data. Yeah, so you maintain the current data. Then after some time, a new data items could be come in, or you need to delete some older data. So that's what we call a dynamic data. You need to consider insertion and deletion operation in your data structure. Yeah. So that's another common requirement in the real world applications, because a lot of real world data is in this dynamic format, dynamic data. Okay. Yeah. So here, when you have a new data item, when you need to insert your new data item into the array, how fast is the insertion operation, right? When you need to delete an older data in your data structure, how fast is the deletion operation? You need to consider. So you can see it's not easy. It's not easy to get a sorting algorithm that satisfies all these three requirements. Yeah. All right, so let's look at the solution this time. Yeah. All right. Yeah, regarding the efficient, this word, because you may feel, some of you may feel, this efficient word could be vague, right? Yeah. So how much do you mean it's efficient? How much do you mean inefficient? Yeah. You need to have some criteria. Yeah. So here, there is a simple criteria here. Yeah. We use the search algorithm. Yeah. Search algorithm, we have linear search and binary search, right? Yeah. 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 So in the linear search, the average efficiency, big theta of n. Yeah. For the binary search, efficiency average, or worst case, log base 2 of n. Yeah, so you see? Yeah. Now we use the search result as our criteria for the efficiency. Okay, here. So if you get the binary search type efficiency, big theta of log n, then we call it efficient. If you get linear search type, big theta of n, not efficient. Okay, yeah. When we talk about individual operations, yeah, so actually this criteria pretty general in algorithms. Yeah. When you work on individual operations, if you can get in general, yeah, because for the special situations that could be different. Yeah, yeah. In the most common situation, yeah, if you can get a binary search type efficiency, then we are very satisfied. Yeah. If you get a linear search type, then we are not satisfied. So usually we feel very slow. So we want to improve. Yeah. And here, our target, this is our target. Yeah. Log base 2 of n. Yeah. All right. Yeah. So, all right. Idea. Yeah. So you need to design your data structure. Yeah. So the first part, the data structure part, design. Yeah. Advanced data structure. Yeah. All right. You need to do a lot of design work in your data structure. Yeah. All right. So here you can see, in order to get a binary search type operation, so you can relate it to the binary search structure. So your data structure should have the binary tree structure. Then you have a chance, so when you search an item in your data structure, then you have a chance to use big theta of log base 2 of n to get it. Yeah. So that's the natural thinking. Yeah. All right. But the question, how do you get a binary tree structure, right? Yeah. How do you, yeah. You know the details of a binary tree structure. But the question, how do you represent a binary tree structure in a simple way? So that is hard. A simple way. Yeah. So let's consider the options we have to construct a binary tree structure. All right. All right. Yeah. The candidates. Yeah. So let's recall the knowledge we learned in our data structure course. Yeah. So there are one candidate array could be a candidate. Yeah. Array, very simple. Yeah. But the main concern of array, we want to see if it can handle the complexity of binary tree structure. Because array is too simple. Binary tree is much more complex than array structure. To make array capable of handling binary tree structure, that's not easy. Yeah. That's a little challenging. Yeah. All right. Another option, linked list. Yeah. Linked list, we know, so because we have a special node link, so we can use, special link node to point to other objects. Yeah. Then, definitely, this data structure is capable of handling binary tree structure. Yeah. But the problem is we need a lot of effort to make it work. Yeah. The linked list is much more complicated than array data structure. Yeah. So we need to compare these two. All right? Yeah. Yeah. But our first option is array. If array can store a binary tree, then we won't want to use linked list. Yeah. Array, because in array we do not need to use pointers, right? Yeah. The concept of pointers. Yeah. We do not need to use that. Yeah. So much easier. In linked list, you need to consider, pointers or references, that kind of concepts. Yeah. Yeah. So we want to avoid. So we want to avoid pointers or references. Yeah. All right. Yeah. So the next technical question we want to answer is, now we want to try very hard to store a binary tree inside an array. If we can do that, if we can solve this technical problem, then we will be very happy. We just use array. Yeah. So we do not need to touch linked list. Yeah. All right. Yeah. So let's try to solve this problem. Yeah. All right. Yeah. But the problem, the array is, if you use array directly, yeah, because we know the structure of array is a linear structure, right? Yeah, it's a line structure. Yeah. So if you look at the array directly, it is a line structure. Line structure, if you manage elements in this line, then when you maintain dynamic data, because when you need to do shift, think about when you insert one data item here, you need to do a lot of shift operation, right? Yeah. That kind of operation is big theta of n. Too slow. So we do not want to do in that way. Yeah. Because based on our understanding of efficiency, we do not treat it as efficient. Yeah. So we do not accept this solution. So we want a better solution. Yeah. All right. So let's consider if we can make the array to do more. Yeah. Our goal, we want to make array to support complete binary tree structure. Yeah. So specifically, so what do you mean? You can store a binary tree in an array. What do you mean that? Because in a binary tree, we know there are many levels, right? You start from the top level, the root at the top. Then you have subtrees, branches, left subtree, right subtree. Yeah. And you need to store the parent-child relationship. That's the key information you need to maintain in order to store a binary tree. So you need to address the parent-child relationship. But in our array, at the beginning, we do not have that support. We do not have anything to address the parent-child's relationship. So we need to solve this technical problem. How to represent parent-child relationship in an array? That's the current technical question. All right. How to modify the array? Yeah. So here, underlying storage structure, that's the array, but you need to add some extra properties on your array. Yeah. You need to add something. Yeah. Yeah. But when you add extra properties, you want to make sure the whole thing is still very simple. You don't want to make it very complex, very messy. Yeah. So you want to make the modification still very simple. Yeah. All right, so that's the idea. All right. Yeah, so the here, so here, this part I want to address, I still want to address the dynamic data operations, efficient dynamic data operations. Yeah, but I already explained. Yeah, all right. So here the new data comes in, you need to recover the order, right? Yeah, yeah, because suppose you want to maintain, order the data. Yeah, you want to recover the order, but if you do it through insertion, through the linear type insertion, you get a big theta of n. Then it's not acceptable. Yeah. But you want to use the binary type insertion. Yeah. When you do insertion, you want to do the binary type insertion. That means you should have a real, because the reason here you have to do this linear type insertion is because you do not store a binary tree in your array, right? Yeah, because for this, the reason is no binary tree structure in the array. If you can really build a binary tree inside an array, then you have a chance to get this efficient operation. That's the main difference. Yeah. That's the main difference. All right. Insertion. Yeah. Insertion, two types. Insertion. Yeah. So now we want to do the binary type, binary search style. All right. Yeah. The question, how to get it? Yeah. All right. Then we need to consider, yeah, so the technical problem we want to work, yeah, how to address the parent-child relationship in using the information in the array, because array we use it as underlying data holder. That means the information we can use from array, that's the array indices, right? Yeah, because that's the only main information we can use to access elements stored in an array through indices, yeah, indices of the elements. So now the question, how to use this indices to address the parent-child relationship? That's the question. Index. You use the index information to define parent-child relationship. If you can do it, then you solve this technical problem. Then you can store a binary tree in an array, because you store the complete binary tree information. You know which node used as a parent node and in which level, then which one child node in which level. You have all that information. That's the idea. Yeah. All right. So let's look at the definition of the parent-child relationship. 8.2. Yeah. All right. So let's work on the typical situation inside a binary tree. Yeah. All right. Here, introduce a heap data structure. First, we need to define a special type of binary tree. Yeah. This special heap structure we call a heap structure. So what is a heap? Yeah. When we call a heap, what do we mean? So it is a special binary tree, not arbitrary binary tree. Okay? We know arbitrary binary tree, that could be very general. So you can draw a binary tree. For each node, you can have 0 child or 1 child or 2 child, right? 3 possible cases, each node. Then any possibilities. There are many different possibilities. Yeah. But our heap data structure, we want to choose a special type of binary tree, not arbitrary. We want to restrict, we want to put some restriction on a binary tree to get a heap. Yeah, what kind of restriction? Yeah, heap. Properties we need, yeah, use array as underlying, yeah, storage. All right. Near, yeah, this is the most important part. Near complete binary tree. So What do you mean near complete binary tree? Yeah. First, you know complete binary tree, right? Yeah. You know what is a complete binary tree. Yeah. So if I draw complete binary tree, each level must be full, all right? Yeah. This level, yeah, for this level, yeah, this is not complete binary tree. To make it a full, you need to draw another node. Okay? Then, if I draw another level, yeah, this is complete. Okay? Yeah. All the levels must be full. That's a complete binary tree. Yeah. But to have a complete binary tree, we know the number of nodes n must be equal to 2 to the k minus 1. So your k number must be in this form. Otherwise, you won't have a complete binary tree. Yeah. That's too limited. Yeah. So when we use array to store a binary tree, we don't want to restrict ourselves so we can only do it for this kind of special n. No. We want to do it for all positive integer n. We can make a binary tree. We store a binary tree with n nodes. N is any positive integer. That's what we want to do. Yeah. So we need to relax the completeness thing. So then we make it, not that strict. So we add a near complete. Not necessarily complete, but it should be close, very close to complete. So what's that? Here. That is, all the levels must be full except the bottom level. Okay? The bottom level we allow. So not full. Yeah. But only the bottom level is allowed. Not be full. Yeah. Not to be full. Okay? All right. All the other levels above the bottom level must be full. Yeah. So we called this kind of binary trees near complete binary tree. Yeah. So our heap must take this structure, near complete binary tree. Yeah. So you may want to ask why, right? Why? Why you want this near complete binary tree? Yeah. Yeah. So the explanation as simple as this. All right. Yeah. So let me explain. So why? Okay. All right. Why? The first thing is, two reasons we use this kind of structure. The first reason, because with this structure, we can represent the binary tree for any n greater than 0, right? Any n greater than 0, then we can use this kind of binary tree to store all the nodes. Yeah, that's the first thing. Second thing, yeah, although we need to store n nodes in one binary tree, but still we have large number of different ways to store, right? Yeah. But why you use this way? Yeah. We have many different ways to store n nodes. Why use this way? Yeah. This way have another nice property. Yeah. Because it's near complete. Yeah. Near complete. All right. Then all right. So there is one thing. The height of the tree, okay? The height of the tree log base 2 of n. Yeah. That's another important reason. Yeah. Yeah. Because we can control. So all the nodes, when we access a node, the maximum number of steps we need is this many, log base 2 of n. Right? That's our target, binary search target, right? Yeah. Yeah. Otherwise, if you do not use this kind of, so if your binary tree is not very balanced, yeah. So this tree is, we can call, so it's near complete. It's near complete, actually it's near balanced. Yeah. The complete case is the most balanced, right? So this is the most balanced. Yeah. Although we cannot get a most balanced case, but we can get this, near most. Yeah, let's say this, near most. Near most balanced. Yeah. Near most balanced, so we can enjoy the result. This is enjoy the result. Yeah. So when we access any node from the root node, yeah, the worst case. So this is the worst case. Worst case we need is the log base 2 of n. That many steps we can access that node. So that's another reason we use the structure like this. Yeah. All right. This number 3 property, sufficient space for dynamic data. That's another technical problem we need to understand. Yeah. So in the real world situations, you may need to solve problems related to this point. Sufficient space for dynamic data. So let me explain the details. Yeah, all right. Yeah, number 4, we can delay, yeah, but I need to find some time to explain number 3 property. Yeah, all right. How much space is sufficient? Yeah, because number 4 we will answer later. Okay. Yeah. Certain relationship among nodes, we will find some appropriate formula for property number 4. But let me answer this question first. How much space is sufficient? Sufficient for what? Sufficient for dynamic data. Yeah. That's some technical question. You may encounter in your real world situation. Yeah. So this is, yeah. Yeah. I hope in case you encounter this situation, you can recall what we learned in this class. Yeah. So what's that? Let me describe a little bit. All right. First, when you need to process, maintain dynamic data, how can you predict how much space is sufficient? Especially at the beginning. It's hard to predict, right? It's very hard to predict, yeah, because the data is dynamic. Yeah. Very hard to predict, yeah. But you have to allocate, yeah, inside your algorithm. You have to allocate sufficient memory storage space for your dynamic data. For example, we know when you use arrays, we know when you define an array, you have to specify the size, right? You have to specify the size. Yeah. Although we know we have some advanced, classes, yeah, yeah, that can handle variable size. We know array is a fixed size data structure. Yeah. Array, you have to, when you define it, you have to tell how large is the size. Specify the size. when you do the memory allocation for an array. Yeah. Yeah. Although you have other, more advanced data structure you can use. Yeah. Vector, list, map, many other. So you don't need to specify the size. Yeah. All right. So here, actually, all those advanced classes, they build on top of array, fixed size array. Yeah. Yeah. They build, the underlying storage structure still array, but they use some advanced algorithm to handle the dynamic complexity. You do not know it. Yeah. It's hidden. Yeah. The details is hidden. You do not know it. Yeah. Yeah. But someone needs to implement some sophisticated algorithm to make it happen. Yeah. Yeah. Here I want to explain that part a little bit. Yeah. Yeah. How much space is sufficient? All right. How to know? Yeah. Then we need to consider all the possible cases. Yeah. All right. How to make array space sufficient for dynamic data? Yeah. It is unknown about the amount of incoming data. Yeah. So at the beginning, you need to define your array size before you know how much data, the size of the data you need to work on in the future. You do not have that information. But you need to make your decision to define an appropriate size for your array. You have to do it. You have to make your decision at the beginning. Okay? Yeah. Do you want to use a very large number or very small number or number, not too large, not too small? Yeah. Right? Yeah. Each decision, you have drawback. You need to consider. Yeah. Yeah. If the array size you use relatively small, then quickly you reach the capacity of your array, then you need to, because after you reach the capacity of the array, your current array cannot accept new data, cannot store new data. So you have to find a way to store the new data. Yeah. But if at the beginning you use some size very large, too large, although you have enough space, okay, to store a lot of data, but if most of the time you couldn't use most of the space in your array, then you waste a lot of memory space, right? That's not good. Most part of the space in your array is not used, so you waste that space. Because as soon as it is allocated to this array, then other software cannot use this space. This space is reserved for your algorithm. So other software, other tools, so they cannot use. Other programs, they cannot use the same locations of the space. Yeah. Then you waste a lot of space. So you need to do it. Yeah. So you need to avoid those two extreme cases. Yeah. Yeah. So you want to find a way to allocate enough space, but at the same time, you don't want to waste too much space. at the same time. Yeah. So how to solve that problem? Yeah. All right. Here I can describe some idea. Yeah. All right. Assign certain amount of space to array initially at the beginning. You just assign, some number, not too large. Yeah, because at the beginning, so you estimate. Yeah, for some period of time, if it's enough. Yeah. So, but do not use too much space. So you do not want to waste too much space at the beginning. Yeah. Because later you can get more space when you need it. Yeah. Yeah. Because when you need it on the fly, then you can add a new space on the fly. All right? When new data comes in, when you fill the capacity of the array, then you use some special way to increase your array size. We know actually the array size, as soon as it is defined, the size cannot be changed. The array size cannot be changed after the object is created. After that array object is created, it cannot be modified, the size. Yeah. But people do it in this way. Yeah. People, when they need to change the array size, so they do not really change the original array size. They create a new array with larger size, and copy the data from the old array to this new array. Then release the memory occupied by the old array. That's the idea. Yeah. So they create a new array object with larger size. Yeah. Then do data copy. Copy data from old array to new array. So after they finish copy operation, then they do not need to use the memory space occupied by old array, so then they release the memory space in the old array. But in that operation, so that's the usual way people do when they need to have more space. Yeah. But in that process, you can see you need to do a lot of data copy work, right? Data copy, it takes time. You copy data from old array to new array. If the array size is relatively large, you need to do data copy work, right? Yeah. Copy one by one. Yeah. Yeah. It takes time, right? Yeah. Think about that. Yeah. Although we know the copy could be very fast, but think about if you have millions of data items in the old array, you copy it to the new array. Yeah. How long? How much time do you need? Think about that. Yeah. All right. Keep adding data and monitoring the size closely. Now we need to fix the technical details. When you do this data copy, you need to take care of a lot of details, right? Technical details. Yeah. So here I want to explain some of the details. Yeah. Yeah. So first, you need to monitor the data. So when you add the data, yeah, because you know the capacity of your array. Yeah. And you know how close is the current storage size to the capacity number. You know that, okay? All right, yeah. But where the current data size is pretty close to the capacity number, yeah, then you need to start doing the preparation for the array enlargement, right? Yeah. Yeah. How much close? You can choose some number that you feel good. Yeah. Here I want to use a line, 90%. Okay. If the current array size equals 90% of the capacity, then can we treat this situation as, very close? You need to start preparation for a new array. How about that? Yeah. Because we don't want to wait the last minute the size equals the capacity. You don't want to, delay your action this late, right? That's too late. Yeah. Too late, that means if you make your decision that late, when you do the data copy, before you finish the data copy, you cannot do anything else, right? Yeah. Everything else is on hold. So you cannot do other things. You have to complete your data copy first. Okay? Yeah. Then you may cause a long delay. Yeah. So we want to start early. Yeah. So we want to start, some appropriate situation. We want to get started. So we have a cushion. Yeah. So we can do the data copy in an appropriate period of time, and we want to avoid a long delay due to the data copy. That's the idea. Okay, all right? Yeah. When a threshold is reached, here, this 90% is our threshold. Yeah. A new array with larger size is created. Yeah. Larger size, usually people double the size, double the old size. Double the old size. Okay? Yeah. Create it. And then copy the data to the new array. Yeah. Yeah. When you reach the 90%, then double the size. Yeah. Yeah. Because in that way, first, you can use this new array quite some time, right? Yeah. Second, you do not waste too much space. Yeah. So you try to find some balanced point in between. Yeah. Not too little, not too much, just somewhere appropriate. So for that reason, you double the older size. Okay? Yeah. All right. Yeah. So then, here I want to, use a simple diagram to explain this data copy idea. Yeah. 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 The idea is very simple, but if you want to implement this idea, you need to write your code carefully. Okay? Yeah. Yeah. Because you need to have this idea in your mind first. Yeah. Then you try to make it happen. So you need to take care of all the technical details. Yeah. All right. So here, this high peak, in this diagram, this high peak, what I mean is, because if you reach the capacity, this case, when you reach the capacity, you run out of space. Then suddenly you need to get more new space. After you get a new space, you need to make the data copy. But when you do the data copy, everything, all the other tasks in your program, you have to pause them. Yeah, because they cannot access data. At this point, the data is not available. When you do the data copy, no other tasks can access your data. So you have to pause all other parts of your programs. Yeah. And when you make data copy, because here we imagine you need to do millions of data items copy, millions in that category. So the amount of time you need to use for this much, okay, this peak, that much, okay, yeah. So think about, if this much in the real world situation, yeah, so let me just imagine approximately 5 seconds. 5 seconds, okay? Millions of data items copy if you need to use 5 seconds. That's quite reasonable, right? Yeah, yeah. 5 seconds. But if you want to make your users, your customers, waiting 5 seconds, that's too long, right? Think about that. When they use your program to do some data processing, suddenly at some point, the program freezes in about 5 seconds. They need to wait 5 seconds. Then after that, then they can start. So that is a very bad experience. Yeah. So you don't want that to happen. You want to improve your algorithm to eliminate that 5 second pause. So you want to handle your data copy in a graceful way. Yeah. People cannot notice. You do the data copy, but nobody noticed that. Yeah. It happens behind the scene, so the users do not even notice that. That's what you want to do. Okay? Yeah. So when you write your programs, so you want to give your customers, your users, customers, best experience to use your program. Yeah. So when you have this situation, okay, handling dynamic data or handling large amount of dynamic data, yeah, not small amount, large amount. So you need to find a graceful way to work on your data copy inside your program. Okay? Yeah. All right, so let's take a break. Yeah, after we start our second half at 7 o'clock. So I can explain that item.